You're planning on buying a new car and you want to learn how the value of the car will change over time. Insurance actuaries predict the future value of cars using depreciation function. Depreciation means the price of a car in general will go down. Okay, so it says the value at 0 years is 24,000. Well, right now in the year 2026, average new car is 50,000. So that's a little bit undervalued there. Let's look at this and see what happens to the value of this car. Could it be a linear relationship? So what happens if I go from 19,440, so 19,440 minus 24,000, so it goes down 4560. So in that first year, it goes down 4560. Then if I look at what happens in the next year, 16,560 minus 19,440 is minus 2,800. And if you look at what happens the next year, 13,920 minus 16,560 goes down 2,640. And then 11,670 minus 13,920 minus 2,250. Now, if this was a linear depreciation, I would expect those numbers to be the same. Since it's real life and not a math problem, close to the same, okay? They're really not close to the same. If you look at it, it looks like I take a bigger hit in year one, and then it gets to be smaller as it goes along. That's in general what happens to a car. Buy a new car, you roll it off the lot, that's your biggest depreciation right there. If I look at could it be exponential, so if I look at the value of the car, let's see what's happening every time. So 19,440 divided by 24,000, so 0.81. So the value after 1 year is 0.81 of the value of when it was new. And then let's just keep doing that ratio. 16,560 divided by 19,440 is 0.85. And then if I look at 13,920 divided by 16,560, that's 0.84. And then 11,670 divided by 13,920 is 0.84 again. So this looks a little bit better. It looks like I do take a big hit that first year. So after year one, my car is worth 81% of what it was new. And then after that, it tends to hover around, 84, 85%. Okay. If I were to try looking at this data graphically and see what it looks like, so let's just take a look at that. So let's look at a graph and so let's look at a table of values. So if I'm looking at 0, 1, 2, 3, and 4, and it looks like the car is worth what, 24,000. Let's just do it in thousands. So 24,000, 19.44, 16.56, 13.92, and 11.67. Let's see what that data looks like. Let's bring that over. So if I look at that data, and here I can see on my graph, so I see the values there. So, if you look at it sort like, well, okay, maybe straight line, but you can sort of, if I start to see what's going on here, I can pretty much see that it probably does have some kind of curvature. So let me get a marker so I can see that. So yeah, let's get a pen, red pen, something like this. So if I try to connect these dots, something like this, okay? What I expect is that it's going to, as the car gets cheaper and cheaper, it's not going to lose the same amount every time, you know, because the car value goes lower and lower. So this appears to be a better exponential model than it does a linear model. So what type of function would best model the car? It looks better to be a exponential model. Would this value of car be a model of growth or decay? Well, it's decay. The value of the car is going down. And so I could decide that, like, okay, I could average all of these guys up. So, and just get an average value. So what would that be? 81 plus 85 plus 84 plus 84. That number divided by 4, about 83.5. So on average, it's 83.5% is the value in the subsequent year. So what would be a model for this scenario? So in this particular scenario, if I'm looking at this, I'm every year is what, 83.5%. And so what's happening is I'm losing. That means you're going to lose what, 17 or 16.5% every year, right? So what would the model for this be? So if I look at this guy, trying to figure out exactly how to do this. Do I want to do it one way or the other for you guys? Let's just go ahead and do it this way. So if I'm losing 16.5% per year, what it means is this number, this exponential number, cannot be more than 1 because that would be growth. So it has to be losing number. So I start out with the value being what? The initial value is what, 24,000. So the model for my car is going to be f of x equals 24,000. And then what's happening? It's losing 16.5% every year. Okay. So what happens if you plug in x equals 0? When x equals 0, the value is 24,000. When x is 1, I have lost 16.5%. When x is 2, I have lost 16.5% twice, and that's how that works. So the exponential growth, well, let's see, what would be the value of this car in 10 years? It's going to be 24,000. And then what is that number? 0.835 to the 10. So I can do that on my calculator. So 0.835 to the 10th, and then times 24,000. I get 3954. 3954 and .36. So that's the value of that car in 10 years. So if we look at exponential growth and decay, in this particular case, if I'm looking at exponential growth, then the value of B has to be greater than 1. I'm growing, okay? And if I'm looking at exponential decay, that value of B has to be less than 1 for it to decay. And so what's happening is you're going to have a formula that, you know, f of x is equal to some initial value, 1 plus r to the x, where r is your growth or decay rate. And if you had f of x equals a 1 minus r to the x, then r is your, this is your decay rate, and this is your growth rate. So anytime like I said, the number in parentheses that's being raised to the exponent is bigger than 1, it's growth. Smaller than 1, it's decay. The population of College Park is about 16,000 people and growing at a rate of 6.7% per year. Create a model P of T that gives the population P in terms of years T. So P is equal to A, 1, it's a growth, so 1 plus R to the T. Well, the initial population is 16,000, so 16,000. And then if it's growing at 6.7%, that's 1 plus 0.067 to the T. Or you can just write this as 16,000, 1.067 to the T. That is my model for the growth of College Park. What does the population predict will be what does the model predict the population will be in 6 years? Well, you just let T equal 6. So you're going to have 16,000 times 1.067 to the 6. So all you have to do is this on your calculator. So 16,000 times 1.067 to the 6. And so population is predicted to be 23,610, 23,6, and if I round it off, 1,1. So that's the predicted population. Now, since I'm talking about people, I don't want to do decimals, so it's going to be a whole number. About when will the population be 25,000? Well, I can see it's 23,000 in the year 6. Let's see what happens when T is equal to 7. So all I have to do there is what? 16,000 times 1.067 to the 7th. And when T is 7, I'm getting, 57,961. So it's hitting 25,000 between 6, and you're going to love this, and 7 years, okay? Now, we're going to get more precise with that in the upper school, okay? You'll be able to tell me exactly when that happens, but with the technology we have and as deep as we're going right now, this suffices for an answer. Most cars depreciate at a rate of 15% per year. Write a model V of T that models the value of a $50,000 car in dollars per year. What would the value be in 10 years? So V of T is going to be equal to the initial value, and then if it declines by 15% per year, that's 1 minus 0.15 to the T. So this is 50,000, and then that's just 0.85 to the T. So in 10 years, all you do is let T equal 10. So my calculator is calculating 50,000, 0.85 to the 10. So I get 9843, 9843.72, value of that car in 10 years. Looking at examples here, this is an example of exponential growth because the number that's in the parentheses is bigger than 1, and this is at a rate of 12% per year. Looking at the next one, this is exponential decay or decline, and 1 minus 0.92 is what, 0.08? So it's decaying at a rate of 8%. This is growth. And that number 2, that is 1 plus 1 to the n. So that's 100% growth. This one is 1 plus 2.01. So again, this is growth at a rate of 201%. This one is decay, 1 minus 1/2. So 1 minus 0.5 equals 0.5. So this is 50% decay. If you were in my class last year, we talked about this topic. Compound interest, it's just an exponential concept as well. The idea that money is invested in interest earned on the principal. So this is the formula. A is equal to P, 1 plus R over N to the NT. A is the future value. P is the initial value or the principal amount. R is the rate of interest converted to decimal. N is the number of times per year the interest is calculated or compounded. T is the time of years. So consider investment of $3,000 invested at interest rate of 8%. Find the value in 10 years, compounded monthly, compounded daily. So A equals P, 1 plus R over N to the NT. So the initial investment, P, is $3,000. The rate is 8%. Time is 10 years. And in this problem, N is compounded monthly, so that's 12. Over here, N is daily, so that's 365. So your calculation here, A is going to be 3,000. 1 plus 0.08 over 12 to the 12 times 10. Over here, it's 3,000. 1 plus 0.08 over 365 raised to the 365 times 10. So on the left, let's see what we get. We get 3,000 times 1 plus 0.08 divided by 12, all of that raised to the 1/20th power. So 665892. Do the same calculation on the right. 3,000 times 1 plus 0.08 divided by 365 raised to the 3650 equals 6676.04. So same interest rate, slightly higher yield when I compound the interest daily. I'm calculating the interest more times. Okay. Rich is comparing the cost of maintaining his car with the depreciating value of the car. When will the cost and the value be the same? So write the formula V of T for the value of the car after T years. So my value of my car, it starts at 20,000. If it's losing 15% per year, that's going to be 0.85 T. Okay. The maintenance is 5,000 in the first year, and it increases by 28% per year. So the maintenance, it starts out costing me $500 maintenance, and then that's going to increase. So 1.28 the T. When would the value of the car equal the maintenance cost? Okay, so let's just take a look at this. I can do this in Desmos. So let me bring up a Desmos window for that. So let's just do another graphing window. So 20,000 times 0.85 to the x. That's my first function. And the other one is 500 times 1.28 to the x. Okay. And I want to look at both of these. So let's look at the windows of time. My x-axis, I can make that go up to say 20 years. My y-axis is the cost from 0 up to, what is it, 20,000? So what I see is the red graph is the value of the car. The value of the car is going down. The blue graph is the amount of money I'm paying to maintain the car. That's going up. So what I'm interested is where do those things intersect? So it looks like at about 9.01 years, so about 9 years and around 4624. Okay. So what is the maintenance cost that will equal the car's value? That's about 4624. How many times will these functions equal? So when will this happen? It's about 9.01 years. How many times will these functions equal each other? Well, the graph tells me that. There's only one time these graphs intersect, okay? Because before they intersect, the value of the car is much more than the cost of the maintenance. After they intersect, the maintenance is more than the value of the car, okay? Um, this is just one time. And then sketching the graph, you could have sketched that. Well, let's just do it. We know that the car starts out at $20,000. So $20,000 is where the car value starts out. And then I know according to my graph, it's going to be just under, so at what, 4,600 at 9 years. So 4,600 at 9 years. So 9 years, 4,600, something like that. So this is the value of the car doing this, something like this. And then the maintenance, remember the maintenance started out at 500, okay? And we know it was going to hit about the same thing here. So the maintenance was doing something like this, okay? Find the equation of an exponential function given 2 points, okay? First case, when one of the data points in the initial value has a domain value of 0. We've been seeing this over and over again. So for example, find the exponential that passes through these 2 points, 0, 10, and 720. Okay, so there's my exponential. F of x equals a b to the x. It's clear that when you plug in a 0, you should get 10. Well, this just tells you a is 10. Okay, so I know that much. Now, I'm going to use the other point to figure the rest of this out. So f of x equals 10 b to the x. When you plug in a 7, your y value is 20. So 20 equals 10 b to the 7th. Divide by 10, 2 is equal to b to the 7th. So b is the 7th root of 2. Now that's not one we walk around on our head very much with. Make sure you know how to do this on your calculator. Sort of a weird way of doing it, but to calculate the 7th root of 2, this is what you do. 7, and then you hit that second key and the little caret key. So 7, and then plug in the 2, and I get 1.104. So I don't want to round this to 1.1, so see I carried 3 decimals there. F of x is 10, 1.104 to the x, because that's this number right here is about 1.104. Okay? You guys should be able to find this next one to figure that out. Now, let's look at the case where we've got an exponential and it doesn't pass through the initial value of 0. Okay? Well, we can sort of fudge it to make it nice and play nicely with us. So let's take, for example, let's rewrite this function as f of x equals a b to the x minus 1. Now I'm going to force that because now when I plug in a 110, I'm going to make that exponent a 0, okay? So if I plug in the 1, I'm going to get 10 equals a b to the 1 minus 1, so a is equal to 10. So I've got f of x is equal to 10 b to the x minus 1. Now the other point is 15, 4. So that means when you plug in a x equal 15, the y value is 4. So I get 4 equals 10 b to the 15 minus 1. So this is what, 2/5 equals b to the 14th. That means that b is equal to the 14th root of 2/5, which is just 0.4. So I need to be able to do this on my calculator. So I just need to find the 14th root of 0.4, and I get 0.9366. So that means my final answer here is f of x equals 10. B, excuse me, not B, I know B now. B is 0.9366, 0.9366 to the x minus 1. So again, it's just handy to force that first value, 110. It's just handy to force that to be the initial value by doing that. So you can do this example here. Since the initial value here is at 7, you're going to let f of x equal a b to the x minus 7. That just makes it easy, then you can figure out the rest of the equation from there. And that leads us up into homework for this section.